how's it going, everybody? I am here on Friday, April 30th. Today we're going to talk about sections 11.8 and 11.9. We're in our very last week of content here. Next week is going to be finals week. So we've got three sections here to wrap up the course. These are super, super interesting sections. I really, really like this last week of this class right here. It's kind of like the most exciting, kind of like culminating idea of this class here. You can see that we're talking 11.8, 11.9 in this video. 11.10 is in its own final video. Taylor and McLaurin series. Awesome, awesome section. And it is one of these things too where I want to say, aside from the fact that it's just really cool, it's definitely the case that like when you leave this class, like people care, like, does this person like know U sub and integration by parts and some series tests, and do they know about Taylor series? Those are like the gigantic four things that people are like mostly interested in the skill being that you have leaving this class. So these Taylor McLaurin series that we're covering in 11.10, really, really important thing that I promise you you're going to see in your mathematical future here. So really important, but also very, very cool sections right here. And honestly, I don't think it's too terribly difficult. I think there's a bunch of algebraic relationships that we need to be able to identify that really aren't too bad. And so I think that you'll find that this is just like a cool extension of the stuff that we've already been seeing out in here in chapter 11, but now is like finally like the super practical end of things. So today we're looking at power series, and power series, hopefully you can just judge by the name, are just a special case of a series, and it is a series where we are looking at integer powers of x. So far all the series that we've investigated, we've just generically denoted them as the sum from typically n equals 1 to infinity of a sub n, in which case we would write this guy as like a1 plus a2 plus a3, etc., right? And here we typically start our indexing here at 1, just because we like to say the first term should correspond to the subscript of 1. One light adjustment that we'll make when we're looking at power series now is these will typically start at 0, just because we typically think of 0 as being sort of the first power that we should consider on x, in that a constant should be our first term in a sum of powers of x. So you can see that our power series still look the same general structure for the sum right here, but what we're going to see now is there's going to be actual variables x involved in the series that we're looking at. So for the first term, I'm seeing just c sub 0, because when I plug in n equals 0 into the x to the 0 is just 1. But for the next term, we're going to get c sub 1 x to the first plus c sub 2 x squared plus c sub 3 x cubed, etc., right? So our power series are just a series, but it's a series that involves all integer powers of x. Or not necessarily all integer powers of x. We'll see some that have some other powers up there. But okay, the amendment I wanted to make was integer powers of x, not necessarily all powers of x. If that was like a 2n as the power right there, then we'd be only seeing the even powers of x, stuff like that. And the thing that is sort of our justification in the previous 5 sections is that we're going to be very interested in whether or not these power series converge or diverge, and we can use all the tests that we built up over the last 5 sections to help us judge that. So we're going to see some of our series tests come into consideration here today. In fact, we're going to look at this like kind of right now, so that we can judge when are these power series going to be good representations of the objects that they represent. When do they converge? And so one thing to notice here, talking about convergence right away, is that you should notice that regardless of what's going on here, regardless of our c sub n coefficient terms, by the way, that's a c because it represents the coefficient on each of the x terms, and you should notice that it really doesn't matter how complicated c sub n gets. This series is guaranteed to converge when x is 0 to the value of c sub 0 here. Because all the other terms will go away. So we get at least that this is going to for sure converge at 0. Right? So let's go ahead and look at the simplest possible power series that we can. The power series where c sub n is just equal to 1 for all n values. Remember, that's the for all symbol right there. So c sub n is just equal to 1 for all of them. So this is the power series of x to the n. So this is just going to look like 1 plus x squared plus x cubed, etc., right? So this is our power series that we're interested in here. It's a polynomial of infinite degree, I suppose. There's an infinite number of terms that we've got. What I'm interested in knowing is for what values of x does this series converge? And what I'm also going to answer right now, although I didn't type it here, is what does this series converge to? So the thing that I'm noticing right here is it seems like this is in the format of a geometric series. Now, when we defined geometric series, we saw that they were written as the sum from n equals 1 to infinity of a r to the n minus 1. And we said it converges to a over 1 minus r when the absolute value of r was less than 1, right? That's what we know about geometric series, right? So in our case right here, we have the sum of x to the n. So it seems to me like we have here, let me write my, oh, sorry. So I want to make one adjustment to this here. So the thing that I'm noticing is this looks to me like a power series because I have a term to the n power, just like stuff to the n power right here. But here's to the n minus 1 power. So I do want to lightly rewrite my structure of my geometric series here. The thing that I'm noticing is that we start by plugging in n equals 1. And what that really does is it causes the first power that we ever experience on r to be 0 because 1 minus 1 is 0. I can build a sum with notationally different that still has the exact same impact here by doing this. If I instead let n be equal to 0, if I could actually write the letter n so it looks like the letter n, a has been unaffected because there's no n's associated with it. Oh my gosh, how many typos am I going to write today? A, R, just to the n power. Now you should notice that this series is literally the exact same series. We just sort of swapped out n minus 1 for n as our notational descriptor here. This is still going to start with this being A times R to the 0 power. Both of the two series that I've written have. And they both have an infinite number of terms. So this is just an alternate representation of our geometric series here, right? So I'm thinking to myself, we're looking for something of the form n equals 0 to infinity a r to the n. We've got something that looks like the sum from n equals 0 to infinity of just x to the n. So it seems to me like we've got here that a is equal to 1, that r is equal to x. And so it seems to me like it should be the case that the sum from n equals 0 to infinity of x to the n should converge to what? Well, a over 1 minus r in this case is going to be 1 over 1 minus x whenever. And here, this was when we had the absolute value of r was less than 1. Well, r is the same thing as x in our case right here. So it seems like whenever x is less than 1, or we could say when x is in the interval from -1 to 1 right there. So here's the weird thing about this here. It seems like this infinite polynomial sequence, when you add up all those polynomial terms, it actually converges on a rational function, but it only is going to converge to that rational function in this little interval near 0, right? So this is really weird, and I'm going to resist the temptation right now to immediately run to Desmos and to show you this graph because in about 20 minutes we're going to be done with section 11.8 and we're going to start 11.9 with this exact same example, at which point we're going to go to Desmos and we're going to see the very satisfying graph. But basically what we're saying here is that if you add up all of these polynomials, or all these polynomial terms right here, it's actually going to converge on a rational function, 1 over 1 minus x, but it's only actually going to match this function, 1 over 1 minus x, in this interval right here, -1 to 1. So what this sort of says to me is this. If I wanted to come up with a polynomial representation of this rational function, I could use these terms here. And the higher accuracy that I want, the more terms I can go ahead and include. All of them, if I want to be exactly correct on the interval -1 to 1. Now, what that kind of means to me is if I wanted to come up with an approximation for this rational function that's a polynomial, like our power series here, but is perhaps accurate near like x equals 5, well, I can't use this one that we have here because this series does not converge on this rational function near x equals 5. So instead, maybe we're interested in shifting where our interval of convergence is going to be. Let's state that word here, interval of convergence. This is something that we're going to identify here in a minute. I'm kind of getting ahead of myself, but I hope that that's a reasonable name for this thing here. It's the interval of convergence. It's where we expect the polynomial representation, the power series, to match the rational function that it is converging onto. So we can shift our interval of convergence by writing our power series in a form that, and I hope that you all just recognize that as a very basic algebraic shift right there. That is a shift by a units to the left or to the right. The negative is built in because it always goes the opposite of our intuition. If it is like x minus 5, that would be a shift to the right by 5. Notice that just like this series up here is guaranteed to converge when x is equal to 0 because it would just leave us with c sub 0. Very similarly, our shifted power series is always guaranteed to converge at x equals a because that would again cause all of these terms to be 0. All we'd be getting left is a c sub 0 right there. A tiny technicality here, by the way, just to kind of mention here. Even when we do have x minus a to the 0, when x is equal to a, it is the convention to allow that to be equal to 1, even though that is technically 0 to the 0 right there. That's sort of a requirement to make a whole bunch of our properties of these series work out a little bit nicely right here. So just a little notational convention. So, in general, there are three possible scenarios then for the convergence of a general power series that is centered. So when I say centered at x equals a, I mean that we're trying to come up with a polynomial that is estimating a non-polynomial. And since it's an estimate, we need to center where that estimate is going to be good near. As we just saw above, we're guaranteed that the estimate is going to be good at the exact center, which was 0. It's then maybe going to be good for some interval around 0. Maybe that interval is going to get really big, maybe not, right? So here's our three scenarios. One scenario is that the series converges only at that one point right there. That would be kind of unfortunate for us because then that means that the power series is not overall a good representation of the function that we're maybe trying to match. The other possibility is the best case scenario, that our series converges for all values of x, meaning we could always use that polynomial to represent the function that is associated with the power series. And that's a good estimate for any value of x. And when I say estimate, I mean maybe exact value as long as you're including all the infinite terms in the series. Finally, the case that is going to come up quite often that we're going to actually need to pay close attention to is there being an interval of convergence. This is our scenario C that you're seeing right here, that there is a positive real number r, the radius of convergence is what that capital R stands for, such that the series converges when our distance that x is from our central location of A is within R, and it diverges outside of that interval. Notice that there is no or equal to on either of those inequalities, and that's because we are only ever going to find a strictly less than statement in this inequality right here ever. It's always going to be the case that the boundary points of the interval, like the -1 and the +1 right there, they're going to need to be checked like sort of individually, sort of by hand, separate from the rest of the interval right there, and we'll see an example of that coming up here in a minute. Right, so these, and I hope that even if you're, I don't know, I understand that we're introducing a pretty new topic here, but even if you're kind of confused about what we're doing so far, I hope that you agree that these are sort of three possible scenarios for like an interval. It either exists at a point, it exists as an interval, or it exists for all real numbers. That's just the three types of intervals that we could have, sort of a point interval, a finite interval, and an infinite interval for where our series is going to converge. So let's go ahead and look at an example here. And we're going to kind of jump into a pretty decent sized example here right away. When I say decent sized, I mean, look at this crazy series right here. So what I'm seeing here is this. I just kind of want to like break down the things that I'm seeing here before we start talking about this interval of convergence right here. It looks like these terms right here are what I'm referring to as my C sub n. That's the nth, a descriptor of the nth coefficient for each of the terms in this power series. Furthermore, it seems to me like this looks to me like an x minus -3, which means to me that a equals -3, which means this series is centered. At x equals -3 right there. And I can see that from the x plus 3. If you plugged in x equals -3, then you're going to get 0 to the n for that term every single time, kind of zeroing out all the terms in the series except for the first leading coefficient out front that doesn't have any x attached to it right there. So that's just kind of identifying the components of this thing right here. So remember, our goal is to decide when does this series converge. And so it seems to me like this is a reasonable place for us to then go ahead and take advantage of our convergence tests. Now, the things that I'm seeing here is that out of all the stuff going on in this series right here, it seems to me like I'm seeing a whole bunch of powers of n and some roots, which are also powers of n. And so it's going to turn out that the ratio and root tests are going to be our friend quite a lot here. So let's remember what the ratio and the root test say here. So what our ratio test said was that our series is going to converge when the limit as n goes to infinity of the absolute value of consecutive terms in the series is less than 1. The reason why this is a really, really useful test for us to use right here is because this whole inequality with the less than 1 right here is going to help us set up a statement of a region where the x value is going to be where we're going to get that interval of x values at which we're going to converge here. So notice that this entire thing, in terms of our generic series, is really like our entire thing is our a sub n right here. In terms of our non-power series, it's just the representation of the entire thing being added up each time. So let's go ahead and do this here. So what we're interested in here is the limit as n goes to infinity of, and this is going to be a big one right here. And it looks like we're going to get negative 2 to the n plus 1 over the square root of n plus 1 times x plus 3 to the n plus 1, all divided by negative 2 to the n over square root of n times x plus 3 to the n. Now, I don't want to have these fractions within fractions right here, so I think I want to kind of bust out some of these terms to be, kind of flatten this fraction a little bit right here. So I think I need to do some keep change flip to get the next guys up here. So I'm seeing all the terms that should be in the numerator are my negative 2 to the n plus 1, my x plus 3 to the n plus 1, and then the square root of n from the denominator down here will get flipped up to the top. On the bottom, negative 2 to the n. I'm aligning all of my terms for myself to do myself a favor before I simplify. I promise you, you're going to see some nasty expressions out here, and you don't want to just botch these with stupid algebra mistakes right here. Be a friend to yourself. Write out an extra line of algebra. Vertically orient your terms that you're thinking you're going to do a whole bunch of cancellation with here. So what I'm thinking to myself now is this limit as n goes to infinity of what do we actually have left here? Well, it looks like just a single negative 2 is surviving because n of them cancel on top and bottom. It looks like a single x plus 3 is surviving. And it looks like we've got this n over n plus 1. Well, I can take the limit as n goes to infinity now. I know exactly what's going on. As n goes to infinity, this fraction underneath the square root is clearly tending towards just the value 1 because there's no noticeable distinction between the numerator and denominator. And the square root of 1 is just 1. So I think I'm okay with actually applying the limit now, right? So I think that I can say that this is just equal to negative 2 times x plus 3 is less than 1. Right? Now, with these absolute values here, what I really want to do is say that this is going to be, therefore, well, okay, I feel a little bit weird making this equal sign and putting the less than 1. But remember, this is what we wanted to say was going on with our convergence right here. We converge when we are less than 1. Maybe it's not quite appropriate for me to throw that in there, but the whole point of me evaluating this is that this expression is the thing that I want to say, oh, when it's less than 1, we'll converge. So And so what I'm going to do now is I'm going to get rid of that equal sign right there, and I'm going to expand my absolute value inequality. So I now know that this should really be negative 1 is less than negative 2 times x plus 3 is less than positive 1. And now I'm just going to go ahead and do some algebra, and I'm going to solve for the interval of x values of which we're going to experience convergence. So I'm going to go ahead and divide everything by negative 2. Notice that by dividing by a negative, I've got to flip the direction of my inequality. and now I'm going to subtract 3 from everything. And so I'm going to get a negative 5 halves is greater than x is greater than negative 7 halves. And so it looks like we converge when x is an element of negative 7 halves to negative 5 halves. All right, so we're not quite done with this guy yet. What we said a moment ago, if I'll let you recall right here, is we just ended up showing that there was a interval over which we converged right there, right? We just set up a statement that was essentially of that structure right there. But what we noticed here, or what we mentioned here, was that the or equal to is missing from this guy right here, suggesting to me we still need to check those actual numbers that we got for our interval of convergence, the endpoint numbers right there. I know that the parentheses version of this is good right here. I still want to check if negative 7 halves and negative 5 halves are going to be in that interval of convergence. I do want to point out to you right now, notice real quick, notice it is centered at 3, just like we said it was going to be. Our interval of convergence was centered at x equals 3, or sorry, at negative 3, which we could have seen and which we already did identify in blue right there. So what we should now go do to kind of wrap this up is we should go and check at the boundaries and see what's going on in our boundaries. So the two values that we need to check are we need to check what's going on when x is negative 7 halves and what's going on when x is negative 5 halves. So if x is negative 7 halves, what do we got going on here? Well, let's go and remind ourselves of what our kind of gross looking series looks like right here. So the only thing that we're doing is we're plugging in x equals negative 7 halves, and we're asking, is it going to converge or not? And notice that there's only one instance of x that we've gotten here. So we're going to throw negative 7 halves in right there, right? So we've got the sum from n equals 0 to infinity of negative 2 to the n over square root of n times negative 7 halves plus 3 to the n. And in this case right here, you're going to see that we're going to simplify this guy pretty nicely. You're going to see there's some nice algebra that's going to make you realize why this is the one of consideration right here. Negative 7 halves. And that's because negative 7 halves plus 3 is negative 1 half to the n. And you should notice that negative 1 half to the n times negative 2 to the n is just 1 to the n, which is just 1. And now my question to you is, does this converge or diverge? You should know. You should know. So I'm going to give you my crazy eyes right here. This guy right here is going to diverge because this is a p-series with p equal to 1 half right there, right? That the power on n down there, that is a 1 over n to the 1 half. We know that p-series always converge when p is greater than 1, and they diverge when p is less than or equal to 1. And so here we are less than or equal to 1, so we are going to diverge. So that says to me, negative 7 halves is still going to keep the parenthesis over there. We are not going to converge at negative 7 halves. Let's go ahead and check out what's going on at x equals negative 5 halves now. Well, you're going to see some very similar things, but are going to pop out ever so slightly differently here. Negative 2 to the n over square root of n, negative 5 halves plus 3 to the n. Well, it looks like this one, write my things the same way as I did last time. It looks like this one's going to have a very similar thing, but now we're getting a negative 1 to the n instead. So now we've got negative 2 to the n over square root of n times positive 1 half to the n. Now this 1 half to the n and the negative 2 to the n are going to lead me to a negative 1 to the n over root n. So you should notice that this is a slightly different scenario than last time. Now we have an alternating series, so maybe we should hit this thing with the alternating series test. Notice that we have our alternating series test. Says, is b sub n plus 1 less than or equal to b sub n? Is 1 over the square root of n plus 1 less than or equal to 1 over the square root of n? Yes. We want to know, is the limit as n goes to infinity of b sub n equal to 0? Is the limit as n goes to infinity of 1 over root n equal to 0? Yeah, it is. So it looks like by the alternating series test, this guy is actually going to converge. So it seems like for this kind of gross series that we are looking at here, that we can conclude and the important thing is that bracket goes right there now because we just showed that negative 5 halves, when x is negative 5 halves, that will result in convergence by the alternating series test right there. Negative 7 halves did not. That was a divergent series. And you should notice it was actually just the absolute value of the negative 5 halves scenario right there. But it seems like if all the terms were positive, that's too much. If every other term is negative, then that was enough to reduce it down to a convergent series right there. So we can use things like the ratio test here. And again, the ratio test is extra good. Remember, the root test is the exact same structure as the ratio test because it gives us this absolute value statement being less than 1, which very much resembles the structure of an interval, right? And we're looking for an interval of convergence right here. And so we're able to find what is the interval. Then we check the endpoints individually to come up with the overall interval of convergence, right? So in general, what we want to be able to do with our power series is identify what is the radius of convergence, what is the interval of convergence, or excuse me, where is the interval of convergence centered, that was at negative 3, and what is the overall interval of convergence right there. So here, notice, by the way, that we found that the radius of convergence was only 1/2 in this case. Right? Because it's 1/2 from the center of the interval above and below to get to the two endpoints right there. All right. So I'm trying to do 11.8 sort of quickly so we can just see the slightly more exciting stuff in 11.9 and then in 11.10 right here. And so the skill associated with 11.8 is really just the definition of the power series and understanding that we can use things like the ratio. I mean, notice like ratio test, alternating series test, both have come up right here, and P series and geometric series. All four of those ideas have all come up already in the 20 minutes so far that we've been talking about section 11.8 right here. So we need to know all those tests right here. So now let's go ahead and see how are we going to go about actually finding how to represent functions as power series. The thing that you should kind of notice that was happening right here is that I claimed when we did this first example that somehow, and I mean, you shouldn't believe this right now, by the way. I claimed that this infinitely long polynomial right here with not even tiny coefficients, like we're going to have an x to the 1 billionth power out here and then more terms, right? I'm claiming that this actually converged to a rational function, which is weird. Now, my next question to you then should be, well, what function does this converge to? I don't know, but I know over what interval it's going to converge on it right there, all right? What we want to come up with now in section 11.9, so 11.9 is going to be like our easy version of 11.10. Well, 11.10 is actually going to be surprisingly easy also. But our goal is going to be to represent certain functions as power series. And sort of the point is this. As we know, there are many functions that don't play nicely with calculus. Either their derivatives or their integrals are very difficult for us to manage. If we can end up representing these functions as power series instead, power series are just polynomials, and polynomials play as nicely as anything could with calculus, right? Differentiation and integration are trivially easy with polynomials. And so the reason why this is valuable to us is because we can now take functions that we can't do calculus with, come up with their power series representation, which is just a polynomial, do the calculus operations with the polynomials, and it should give us results that are equivalent to having done the calculus with the original function, which we technically can't do, right? So what we want to do now is see how do we come up with some series that are representable, or come up with power series to represent certain functions. We're only going to see special cases here in 11.9 to kind of give us the flavor of it, and then we're going to generalize it to make this work for any differentiable function in 11.10. However, the thing that I want to keep reminding you is that this interval of convergence is telling us where is the power series actually going to be a good representation of the function. It seems like whatever function this guy represents, the power series that we've expressed right here is going to be a perfect representation of that function within this interval. But away from that interval, it's going to not necessarily be a good representation of that function, right? So aside from just hoping to come up with these power series, I'm also hopeful that they will have very large intervals of convergence, perhaps the entire real number line, to say maybe we can come up with some power series that are literally just straight up equal to a function at all values of x. That would be really, really valuable, right? So in this section, we'll see some of the easy to find power series. Although what I want to say is that this one amounts to a sort of like doing some like algebra. They're not tricks right here, but it's like recognizing special forms of things. I honestly think this will be actually more easy once we get to 11.10, the Taylor series up there, because we just get a general formula for how this works for everything. Right now, we're going to like pick out some special ideas here instead. So it turns out there's some power series we already know how to build based on what we know about geometric series, and we've already done this. You should recognize this as the example that we just did like 25 minutes ago right there, except we're going to do it backwards now. Remember that these are the facts that we know about geometric series. We write them as AR to the n minus 1 when the sum starts at 1. Alternatively, we could start the sum at 0 and write them as AR to the n, right? These converge when the absolute value of r is less than 1, and what they converge to is a over 1 minus r, and they diverge otherwise. So let's consider the function 1 over 1 minus x. If I said to you, hey man, I want you to come up with a power series for the function 1 over 1 minus x, you should say to yourself, wow, this looks a whole lot like this thing that I know that we get out from geometric series. This looks like a over 1 minus r, which is exactly what geometric series converge to when they do converge. Well, I'm thinking to myself, in this case right here, it looks to be like a equals 1, and that r equals x. And again, remember, we identified this exact same stuff 20 minutes ago right here. So it should be the case that the series n equals 0, the infinity of ar to the n equals the series n equals 0 to the infinity of 1 times x to the n, which is, and I'm just writing this to kind of make absolutely sure everybody sees where these terms are coming from, converges to 1 over 1 minus x when the absolute value of x is less than 1, or we would say negative 1 is less than x is less than 1, or x is in the interval negative 1 to 1. Right? So because the fact, so notice how special this one is right here. This is like what I was saying, that this is almost like cheatingly special. We are looking to hopefully do this type of thing for like all functions. And right now, the first one that I gave you, oh, what do you know, is like identical to the structure of things that we get out from geometric series. So I was able to say, oh, well, this is clearly could be written as this geometric series right here. Once these don't look like this, like when I give you e to the x, what are you going to do? E to the x doesn't look anything like a over 1 minus r, so we're not going to be able to do like that special case of it right here, right? So this is sort of the specialty ones right here, but we're trying to get a feel for what's happening. So I want us to go now look at a picture. And by the way, we're going to do a whole lot of Desmos in the rest of this video and going into the next video right here. We really, really want to see what exactly is happening, and I want to show you some Desmos functionality that I'm assuming most of you didn't know about, because I didn't know about it until the other day as well when I was getting this video ready. So what I want to show is, what does it mean that we say that this series, the series x to the n, converges to 1 over 1 minus x in this interval right here? Let's go ahead and take a look at this guy right here. So I'm going to open this guy up. Oh, you stupid thing. Give me the different one right here. Okay. And here we are. So here's what I'm seeing here. So one thing I want to show you guys is that Desmos can do sums that look like this right here. And in fact, I'm just going to delete this just because I don't even know why I like linked this in here. So what we could do is I can really just type y equals, and I'm literally just going to type the word sum, and it automatically just gives me that, right? So I want to let n be equal to 0. But what I'm going to do, rather than putting like an infinity up there, is I'm just going to let this be a, because I want to choose how many terms of my sum I am interested in discussing. I'm going to do x to the n, and you should notice that that n equals blank was built into the sum, so it expects parameters that look like n, right? And so here's the thing that I want to show you. I want to change this. I want this to be able to go from 0 to 10 with a step of 1, I think is fine right there. So remember, our goal right now is we want to come up with an estimate to the function 1 over 1 minus x. All right. We're centering our estimate. Notice that this doesn't have like an x minus a term. It's just x. So you should think of that as like x minus 0, meaning this is centered at x equals 0. So what that means to me is I first want to come up with a 0-degree polynomial that matches the function 1 over 1 minus x when x is 0. Well, a 0th degree polynomial is just a constant, and so it makes sense that we're getting a horizontal line that exactly matches the height of the function. So the y value at x equals 1 is matched. Now, when we introduce our second, so this is right now just the function y equals 1. That's all we're getting. Now I'm going to say, let's bring in our our next term, our first linear term right here, our first term that actually has an x in it. Now I'm saying, not only do I want our power series to match the function value, I also want it to match the first derivative. You should notice that this red line is a tangent line to this curve right here. Then we're going to say, you know what? I don't just want it to also match the value and the first derivative at x equals 0. I also want it to match the second derivative at x equals 0. So this is our second order approximation to 1 over 1 minus x. This would just be the function 1 plus x squared right here, I believe, is what we're looking at in red right there. And what I want you to see happening is that as we introduce more and more and more terms, this polynomial is fitting more and more and more nicely to the green curve right there. But it's only doing so in this interval from like -1 to 1, where we consider it to be a good approximation. And outside of that interval, it seems to be doing a terrible job of approximating the function. I'm only letting this go up to 10, but I hope that you're down with the fact that if we're out there at 100, that we're going to be getting more convergence out there. And you should notice, where does it seem to be diverging away and no longer being a good representation? At -1. Notice that we're not quite at -1 right here, but we're also only at the first 100 terms of what should be an infinite series out there, right? So I wonder, will it do... Did it do that right there? Does it not understand that? Summation bounds must be finite numbers. All right, well, can I just do like this, or is it going to freak out at me? Okay, I guess it kind of did it right there. So the first 100,000 terms, and we can see we're like a perfect match for the function in green, essentially between -1 and 1. We can go up and check this one as well. Oh my God, okay. So when I put in 100,000, it's now trying to do some like x to the 100,000 stuff out there. It's struggling, but you can actually see when I clicked right there that it's clearly sitting right, oh man. Yeah, Desmos is losing its mind right now because I just typed in way too big of numbers for it to be able to think anymore. In any event, I think that you kind of get the picture right here, which is that this thing is, all right, let me go back to the A version. Oh no, now I did it. All right. Relax, Desmos, relax. Oh man, now I did it. Okay. Well, in any event, I like crash Desmos here. There we go. So what we're doing here is every time we include a new term in the series of the infinite series, we're getting a slightly better approximation, and that approximation is always centered at that x equals 0 location. That's where we're getting exactly correct. The further away from x equals 0 we go, the more error we have, but we're mitigating that by including more and more and more terms in our power series. It is converging on that interval -1 to 1 to be exactly the same as that rational function. Outside of -1 to 1, it is not exactly the same as that rational function out there. That's what we're seeing. All right, so super cool right here. Really, really, really weird that we can come up with a rational function using only a polynomial. It only matches for a tight little window, but it matches like exactly if we include an infinite number of terms. It literally converged onto that function over that interval right there, as long as we include all the infinite number of terms in the series out there. So that's pretty cool. Um, so that one was easy because 1 over 1 minus x is in the exact format of the value of a convergent geometric series, a over 1 minus r. So let's look at ones that are a little bit further away right here. Let's extend this idea, and let's go ahead and find a power series for this slightly grosser rational function right here, x to the fifth over x minus 5, and let's determine the interval of convergence of this thing right here. So what we want to do in this case here is, get out of your keyboard. We want to force x to the fourth over x plus 5 to look like 2 look like a over 1 minus r. So it seems like we need to determine what's going to be a and what's going to be r. And I think the thing that's bothering me the most so far about this is that 1 sitting right there is associated with the 5 right there. So I guess the first thing I want to say right away is it looks like a could just be x to the fourth, right? That's just the numerator term right there. I think I'm okay with that. What else are we going to do here? So how are we going to deal with this denominator, right? So let's kind of suggest to ourselves that we've dealt with x to the fourth, we've dealt with the a. I really just want to think about this as maybe being something instead like x to the fourth over 1 over x plus 5. So what I want to do is I want to get this into this form 1 minus blank right here, right? So I'm thinking that if I'm going to turn 5 into 1, I need to do a 1/5. I need to factor out that 5 from the denominator down here. And so I'm going to factor out a 5 from the denominator. And that's going to give me, and I'm going to write this in the other order, by the way, 1 plus x over 5. And what I really want to write this as is x to the fourth times 1 over, or excuse me, now I'm going to write this ever so slightly differently. X to the fourth times 1/5 times 1 over 1 minus negative x over 5, right? So I got out my algebraic beating stick, and I forced this thing to look like a over 1 minus r. I've got it now. A over 1 minus r right there. So I think that I can then go ahead and conclude that this must be something like x to the fourth over 5 as a coefficient out front times the series n equals 0 to infinity of a is 1, so I've got 1 sitting right there. R is negative x over 5, and so I think I'm going to get a negative x over 5 to the n. There we go. This is just some algebraic manipulation. Now, one thing that's really important to notice here is that this x to the fourth, this was acceptable. I kind of said that a could just be x to the fourth, which would lead you to believe that the x to the fourth should be inside the sum. But remember that the sum is controlled only by n, which means that this is independent of n, this x to the fourth and this 1/5 term right here. So these could either be inside the sum or outside the sum. Recognize that being inside the sum means every single term is going to get that extra x to the fourth on it. But what you know is that if a polynomial has a factor of x to the fourth in every single term, then it might as well just be factored out to the front. And that's exactly where I've got it sitting right now, is that x to the fourth being factored out right there. It's all the terms that involve n that can't just be moved in and out of the sum. But since x to the fourth divided by 5 was independent of n, it doesn't matter if that multiplication happens inside or outside. We could just pull it outside. It's just like a constant multiple with a derivative. You just could ignore it for the purpose of the application of that process there. This is our way that we can force this slightly less comfortable looking function to be written as a power series here. And what we want to see is, let's go ahead, let's take a look and see what this looks like in Desmos as well, by the way. So x to the fourth over 5 times the sum from n equals 0 to infinity of negative x over 5 to the n. So I'm thinking that this is going to be looking like here. And I mean, so what I'm doing right now is I just want to write out a couple terms of this series so we can kind of get a visual. This just looks difficult for me to interpret right here. So let's just kind of do a few terms, right? When n equals 0, we're just getting 1 from this guy. But it's going to get multiplied by x to the 4th over 5. So I think my very first term of my series is x to the 4th over 5, right? This is when n equals 0. Our next term, when n equals 1, when n is 1, notice right away we're going to get a negative value for this guy. We're going to get a negative x over 5 times x to the 4th over 5. So I think I'm going to get a minus x to the 5th over 25. Now, when n equals 2, I'm going to square this, so it's going to be positive again. X squared and x to the 4th gives me x to the 6th. And we've got 5 is squared down here times another one. That's going to give me a 125. And then a minus x to the 7th over 625. So we're claiming that this series right here is actually the same thing as this x to the 4th over x plus 5 right here. So let's go ahead and take a look in Desmos to see that we're actually getting that type of behavior right here. So our claim is that y equals x to the 4th over x plus 5. Here's my new function in green that we're trying to match with the power series. Our claim is that I should be able to write this as x to the 4th over 5. And this should really be negative x over 5 to the n, right? And so what we want to do now is think about, wait a minute, start me at 0 here, dang it. So notice here that when n equals 0, we're just getting x to the 4th over 5. And that turns out to be a great approximation of this guy kind of right away. Even when we're only looking at the very first term, it's a pretty good approximation. Then as we increase the number of terms that we have, so it's kind of wonky because now it's an odd polynomial kind of fitting this thing. So it's got that leg dropping down on the right. So it's bad far away, but it's getting even better in the short term right here. And you should notice by like even only including the first man, like I can see a bare smidge of green versus the red right there. These are probably the worst colors I could be using. Let me pick my orange and my blue as is appropriate right there. So I can see this bare smidge of orange right there with only 5 terms being included right there, right? That's excellent, right? As soon as I have 6 terms, literally the entirety of this graph being covered on the screen right now is perfectly overlapping right there. So it looks like this is doing an excellent job right here of estimating this series, of estimating this rational function. And again, this series is a polynomial series. It's estimating a non-polynomial function. It's doing literally nearly a perfect job in a pretty wide window around the origin right here. And then it seems to be obviously diverging as we get further away. It's not doing as good of a job as we get further off right here. Notice, by the way, if you're looking at these being close together, what you're seeing is this horizontal thing. What we're always measuring is what are the outputs, how are they comparing to one another? And you should notice that if you're looking for like this height here, where do we get, what value are we at the same x value on the orange curve and on the blue curve? You should notice that these actually have like massive amounts of vertical error. That's where we're measuring our error. Vertically, there's a whole crap load of error right here because this is such a steep function. So this is quite a lot of error that we're getting out here. But again, near the origin, we're doing a perfect job of estimating this rational function with a polynomial there. Right? So let's see here. Oh, I guess we check? We didn't check for the interval of convergence here, right? Let's check this real quick. Convergence. Let's check out the ratio test again because all we've got is powers of n. Limit as n goes to infinity of the absolute value of negative x over 5 to the n plus 1 over negative x over 5 to the n is clearly the limit as n goes to infinity of, and all we're left with is just a negative x over 5, right? We want this to be converges when we're at less than 1. I don't know why I just wrote 0 right there. And you should notice that this limit, there's no n's involved. We literally cancel them all away right there. So we're just getting that we're going to get this negative 1 is less than negative x over 5 is less than 1. And it looks like this should be converging on the interval x is an element of negative 5 to 5 right there. All right. We should check the endpoints. I'm not going to go ahead and check that right now. I'm going to move on to our next idea. So I'm just going to say still need to check endpoints. We can see we got a little bit bigger of an interval of convergence than we did in the previous problem, right? Before it was negative 1 to 1, here it's negative 5 to 5. So I'm just going to not do that algebra work right now. I know that you guys can throw in negative 5 and positive 5 and determine if those are going to converge for yourself or not. So again, ratio test generally super helpful with a lot of these guys right here. And if the ratio test isn't it, check the root test. Let's get some more good news. The whole reason that we're doing this is because we want to come up with functions that are going to play more nicely with calculus. And the good news is that because power series are just polynomials in x, we can perform differentiation and integration term by term on those series, which means it's acceptable for us to just perform those derivatives and integrals on the a sub n expression within the sum itself, rather than having to like I don't know. This is just saying since the series just represents a big old sum, and you know that derivatives and integrals are okay to be performed collectively over a sum or individually term by term, that we can just go ahead and perform derivatives and integrals on just the a sub n term with a series. So we've got some kind of gross looking series right here. This is called the Bessel function. It's very, very useful for some applications in physics. Doesn't matter. I'm just trying to show you that we can take the derivative of a series and we can take the integral of a series, and it's going to work out just kind of like you'd hoped. Just remember, the important thing here is that we do have this like n equals 0 to infinity on the sum. This sum is controlling the n terms. But x is still really the variable associated with our function that we're plugging in. I am taking my derivative with respect to x. So x is the only thing that matters when I take my derivative. So here we should just be getting out this series from n equals 0 to infinity of negative 1 to the n. I need to take my derivative of x to the 2n. So it's going to be 2n times x to the 2n minus 1, all divided by 2 to the 2n, n factorial squared. Is it weird that an n factorial squared would ever like naturally arise in a formula that describes physics functions? That's just so weird to me. In any event, same exact thing with integrals. Don't forget your plus c. That's going to be my only kind of warning about these ones right here. N equals 0 to infinity, same deal, right? This is basically just saying take the integral of x to the 2n. We know we're going to add 1 to the power and introduce that fractional coefficient of that same power right there. So I think I'm going to just get a x to the 2n plus 1. And then down here in the denominator, we'll get a 2n plus 1 term as well. All right, so there's my integral terms sitting right there, right? And I just shook my fist at you, so I better write it for myself. And I'm going to say, don't forget. Sometimes that c term is going to become some meaningful term for us right there. All right. So one, this is just saying this is awesome. You can take derivatives and integrals of series just straight up as you see them. You don't have to think about the individual terms. And even better, we'll be guaranteed that the radius of convergence will remain the same for the series after applying a derivative or integral. However, it is possible that the interval of convergence may change, meaning it's possible that one of the endpoints or both of the endpoints might change their behavior, converge, diverge. But the interval itself will remain the same. If you were an interval that was 5 units up, 5 units down, that will still be the case after you take a derivative or integral. It might have been the case that before you converged at your endpoints, now maybe you diverge at your endpoints because you took a derivative or an integral, so you still might need to double check your endpoints. But this is good. This is basically saying our behavior should remain the same when we take our derivatives and integrals of a power series out here. And it turns out that this is a very, very useful thing for us in our search for power series of more complicated functions. So what we've been saying is that it seems to us like as long as we can get out our beating stick and make something look like a over 1 minus r, that's the only way that we know how to make a power series so far. But now what we know is that we're going to get that same radius of convergence, and we get derivatives and integrals are acceptable to be applied to these sort of things. So this is going to like help us in our manipulation game. Now instead of just doing algebraic manipulations to make it look like a over 1 minus r, now we can also do calculus manipulations. We can take derivatives and integrals to make things look like a over 1 minus r if we want as well. So you should immediately notice then that we've got sort of like a problem with this very first one. This is not in a form that can be forced into this a over 1 minus r, right? So So my deal here is this. I can't get this thing to look like a over 1 minus r because I have sort of like a over 1 minus r squared. There's no way for me to just get rid of a square, right? I can't just algebraically manipulate that away like we just factored out a 5 in the previous example. However, we now have seen that it's acceptable for us to use calculus operations pretty simply in association with these functions here. So watch out this tricky little maneuver here. So what I'm going to do is I'm going to go ahead and, yeah, I wasn't even close to giving myself enough room for this one, is I'm going to go ahead and take the integral on both sides here. And you should notice, what are we going to get from this integral right here? Well, when I do this integral right here, this is really like the integral of 1 minus x to the negative 2. So I'm going to add 1 to the power. So the power becomes negative 1, which is exactly what I want. A negative 1 is going to pop out front from the integration. But also, because I technically should do a u sub, we're going to get getting a negative popping out from the inside right here as well. And this is actually going to be giving me 1 minus x to the negative 1 plus c, which is really just 1 over 1 minus x plus c. All right. So it looks like while we are not an algebraic manipulation away from looking like a over 1 minus r, we are just a single calculus manipulation away from looking like a over 1 minus r. So I'm going to use some calculus to help us get us there, right? So it looks like we just found that the integral of the function that we're looking for is 1 over 1 minus x plus c. And it's really the case that I already know what the power series is that this looks like, right? This is really just the series n equals 0 to infinity of a is 1, r is x. That's just our x to the n plus c, right? But remember, we wanted to come up with a series for f of x, not with a series for the integral of f of x. So now what can we do? Well, now let's take a derivative on both sides to undo that integral that we did. Well, this is just going to leave me with f of x right now. That is the 1 over 1 minus x squared. And it should be the case that I'm going to take the derivative with respect to x, which means we're going to get the sum from n equals 0 to infinity of n times x to the n minus 1. Plus c just went away to 0 in this case right there. And this is the power series for f of x equals 1 over 1 minus x squared. And we also want to know about the associated radius of convergence with this guy. And we can say because x to the n has a radius of convergence of 1, so does nx to the n minus 1. Right? So that's kind of what are we concluded about. When you take derivatives or integrals, it does not alter your radius of convergence. These are both centered at 0 because we don't see that like x minus a term. We just have simply x sitting right there. So this seems like this should be the power series for 1 over 1 minus x squared. Let's go ahead and take a look. So we are now looking at, we've got 1 over 1 minus x squared, and we just made the claim that this should be looking like y equals the sum from n equals 0 to a of n times x to the n minus 1. And let's go ahead and, god damn it, just get up there. Minus 1. Oh my god. That's killing me today. I want this to go from like 0 to 10, maybe, with a step of 1. Importantly, remember these got to be integers. That step of 1 matters right there. So what we wanted to, let's go ahead and see here. Oh man. Oh, there we go. Oh yeah. Oh, ooh, that's nice. Ooh, yeah. So satisfying right here. So again, our green curve right here we can see is converging onto the blue curve right here. Only in the first, right now got the first 9 terms out of the infinite number of terms being included in the series. You can see that we're really only doing a great job of converging within about a half on either side right there instead of 1. But if we were to increase this to more terms out there, you can see going up to 90 terms, it seems pretty clear that we are getting much, much closer to -1, where we're going to be a perfect match for this function, right? And when I say perfect, it's not exactly perfect, but damn is it close. And it stays close the entire time that we're in this -1 to 1, almost up until the endpoints right there. And again, that's because I'm only using the first 90 polynomial terms out of an infinite number of polynomial terms. If we included all infinite number of terms, then we would get identical matches for the function values between the series and the original function between -1 and 1. So again, what we're doing is we're trying to build polynomial series that are representatives of non-polynomial functions, generally because it's mostly easy in life to do math with polynomials and not with pretty much anything else. And again, if we wanted to come up with a polynomial function that represented this non-polynomial function elsewhere, if I wanted this to be a good match like x equals 3, then we could have just built our power series to be centered at x equals 3 instead of at x equals 0. Oh man, Desmos is just losing its mind right now. Even this is a lot of computation. Doing 90th order polynomials, stuff like that is a lot of computation that Desmos is doing right here. So don't be surprised if you like break Desmos and have to click reload. Doing massive numbers is not going to be super helpful to you right here, but I think I'm hoping that you're kind of like getting the gist of what's happening here. Oh yeah, I'm sure I just broke it right there. I shouldn't have even done that. And I think it's valuable to like watch the growth happen, right? I'm saying what's the best first order polynomial? Ooh, now okay. So I was seeing something weird happen right here, and that was this. Here's the thing that I thought was a really strange thing that was happening right here. It was this whole n equals 0 thing. Why is this a weird thing that's going on right here? Why do I think it's weird, and why is it actually okay? The reason I thought this was really weird when I saw the a equals 0 is because I said to myself, we're trying to match the function at x equals 0, so shouldn't its first term be the height at 1? Since the function is a height of 1, why would our estimate have a height of 0? It's a terrible estimate getting started. And then we went to here and we got that. Why? Well, you should notice that when you plug in n equals 0 into this guy right here, we're actually looking at a 1 over x term right there, which is not associated with power series. Power series always has positive integer powers or non-negative integer powers on this thing. So it seems like it's actually only appropriate for us to be starting this guy actually at 1 to cause x to the 0 to be our actual first term in the series right there. So that's why this was giving us a very, that seems weird to me. That green line's wrong right there. It's a bad estimator of the blue curve at x equals 0 because it should have just matched the height, which it does when we go to actually the first term in the series, which is a equals 1 right there. And then we get our linear, which is just a tangent line. This is just our tangent quadratic. This is the best possible quadratic approximation to this rational function centered at x equals 0 right here. We get our cubics, our fourth order, fifth order, right? Stuff like that. So every time we introduce a new term, we match it for like a little bit longer. We match another derivative of that function as well, right there, which is really cool. So let's see, on to our next example here. So the next one is the natural log of 1 minus x. And I'm hoping that based on the previous, our next example is the natural log of 1 minus x. And I'm hoping that based on the previous example, you can kind of see what trick we're going to do right here. Remember that the only things that we know about are a over 1 minus r. That's the only thing we can handle right now. In the next section, we're going to get everything else, things that can't be put into that form. Obviously, there's no algebra that we can do to make natural log of 1 minus x look like a over 1 minus r. And so then I ask you, is there any calculus you could do to this thing to make it look like a over 1 minus r? Well, I know that you guys know that we can take the derivative of this guy and get negative 1 over 1 minus x. All right, we're going to get 1 over 1 minus x times the derivative of the inside function, which popped out that negative there for us, right? And so I know what power series this looks like. This must just be the series from n equals 0 to infinity. A is 1, so there's just I'm not going to write it, it's a multiplication by 1. R is x, so we're just going to get a x to the n right there. That seems to be the power series for the derivative of the function of interest right here. So we get that the d dx g of x is going to be equal to the negative, the sum of n equals 0 to infinity of x to the n. So what we didn't want was the power series for the derivative of g. We wanted the power series for g. So what are we going to do to recover it now? Let's just go ahead and integrate both sides. We recover g of x on the left-hand side because the integral of the derivative is the original function, give or take a constant shift, which I'll include on the right-hand side over here. And it looks like here we are going to add 1 to the power, so I think I'm going to get a negative 1 over n plus, I got to get this inside of my sum, hang on. Negative sum from n equals 0 to infinity of 1 over n plus 1 x to the n plus 1 plus c, all right? Oh yeah, so I do want to write this a smidge different here. So notice a little bit of a thing that is very, very, very common right here is in general, and I'm going to do a whole bunch of scrolling here, 1 second. In general, people really, really like to represent power series in this format right here. And you should notice that the important thing about this format is that we're always doing n power whenever possible. And so my question to you is, how can we manipulate this so that it looks like it's just written to the n power? Right now we have an n plus 1 power. So I'm noticing that if we were to plug in n equals 0, the first power we should be experiencing on x is 1. So it seems to me like I could instead just start my series at 1 and write this as 1 over n x to the n plus c. Now I'm starting at 1. I'm still getting 1 over 1 times x to the 1. That's exactly what I got over here when I plugged in 0. We're starting at that exact same first term right there. So this is a slightly simplified version of the series where we modified the bounds on the sum to make the value, the a sub n term inside the sum, be slightly simpler right there. So now the question is what's up with c? And then we'll do our last one. Since negative sum from n equals 1 to infinity of 1 over n x to the n plus c is supposed to approximate natural log of 1 minus x, I left an important detail here, with the center of approximation being centered at x equals 0, the values should match at x equals 0. So I'm going to say here, natural log of 1 minus 0 is the natural log of 1, which is 0. And similarly, negative sum from n equals 1 to infinity of 1 over n to the 0 n plus c should therefore be equal to 0. And it looks like this is just 0 plus c equals 0. So we're going to get that c is going to be equal to 0. So we can say that power series for g of x equals natural log of 1 minus x is, I'm not going to write that as g of x since it doesn't converge everywhere, is negative sum from n equals 1 to infinity of 1 over n, x to the n. And we can all, and again, I think it's a good move to kind of like always write out some terms for these guys right here. So notice we start at 1, so we're just getting negative x, and then we're getting minus x squared over 2, minus x cubed over 3, minus x to the 4th over 4, etc., etc. Let's go take a quick peek in Desmos and see that that is going to be remain the same. Actually, sorry, before we go to Desmos, I want to show you another cool thing with this guy right here. All right, so we know it converges on negative 1 to 1. So what that means to me is I can use this infinite series to represent values of natural log of 1 minus x as long as I'm choosing x values in the interval from negative 1 to 1. So let's use this to estimate some rational numbers here. Write this ever so slightly differently, to find rational estimates of irrational numbers. So check this out. Let's go ahead and say that ln of 1 minus x is straight up equal to the series n equals 1 to infinity 1 over n x to the n. Sorry, the negative is sitting right there. For absolute value of x less than 1. That's where it converged. So therefore, when x is 1/2, this series should be a perfect representative of the natural log function. So let's go ahead and do it. Then that should mean to me that the natural log of 1 minus 1/2 is equal to the negative sum from n equals 1 to infinity of 1 over n times 1/2 to the n. This is going to be the natural log of 1/2, which, by the way, you should notice is the same thing as the natural log of 2 to the negative 1, which is the same thing as negative natural log of 2. And what are we getting from the series right here? Well, I'm going to go ahead and I'm going to get, when I plug in n equals 1, I'm going to get negative 1/2. When I plug in n equals 2, I'm going to get a 1/2 times 1/4 is 1/8. When I plug in n equals 3, I'm going to get 1/3 times 1/8 is 1/24. When I plug in 4, I'm going to get 1/4 times 1/16, which is 1/64. And so it looks to me like we just came up with a good estimate for the natural log of 2 in terms of an infinite series of fractions. And this is straight up equality, right? And by the way, I'm dividing by a negative on both sides. If we include this infinite number of terms, this is now an infinite series that gives you literally the number natural log of 2, which is kind of crazy. And isn't this the 0.693 that I feel like I learned in chemistry class or something like that a long time ago? So I mean, this is just sweet right here. This is an infinite series of fractions, of unit fractions, that is literally straight up equal to, not an approximation of. Those dot dot dots say if you keep going infinitely far, you will literally converge on the number natural log of 2. And I know that we'll converge on it because x equals 1/2 is within my interval of convergence right here. So let's go check this guy out over here in Desmos. We were just saying that the natural log of 2 should be equal to the sum 1/2 plus 1/8 plus 1/24 plus 1/64. And look at how close we are. In just our first 4 terms right here, we're getting a 0.6822 instead of a 0.693. So right now we're off by about 0.01, right? Which I don't think is terrible considering we just only did 4 terms of an infinite series here. And we could check this even further and just do the sum from n equals 1 to, I don't know, let's do 1,000 terms right here. And what does our series look like right here? I'm forgetting. We're looking at 1 over n times 1/2 to the n. And look at that right here. 0.693147, 0.693147, 18056. So in the first 1,000 terms of this series, our decimal expansion literally matches exactly what natural log of 2 is for all of the decimals that Desmos shows us. We just got 10 decimals of precision. And I mean, honestly, I bet we could even chop that down by a lot. And it does, so I just chopped off even just the first 100 terms right there still matches the natural log of 2 exactly to the first 10 decimal places out there. That is freaking awesome right here. So what we're doing is, again, we're coming up with these expressions that might be difficult to do math with, and we're coming up with ways to re-express them that is simple to do math with. We just came up with a rational estimate for an irrational number that we can make as precise as we want. We can only make these estimates for small values of natural log that are within that interval of using x values between -1 and 1 with the function natural log of 1 minus x, but we could have shifted this and just built our power series to be centered elsewhere with that shifted x minus a term, and we would have then just been able to make those approximations elsewhere instead. So really, really cool, really, really powerful stuff right here. The fact that we can write essentially any function as a polynomial, the fact that we can estimate irrational numbers with rational numbers, really, really, really powerful tools that we're getting right here. And this is why power series and Taylor series that we're going to see in the next video are used so extensively everywhere, is because they convert difficult things into easy things. The easiest family of functions to do math with, period, is polynomials. Power series converts non-polynomial functions into polynomial functions. The easiest types of numbers to do computation with are rational numbers. This can help us convert irrational numbers into rational numbers. It's true that we then have to contend with the fact that it's an infinite series that's representing that stuff out there, but each of the individual components is very easy to work with. We've got fractions, we've got polynomials. Are there easier numbers to do math with and easier functions to do calculus with? There isn't. So this is really kind of converting everything into our best case, simplest type of scenarios out here, which is really, really cool. So let's go ahead and see one last example here, and we will call it a day. So tangent inverse of x. So I hope that you are down with the process that we've been doing here to say, obviously there's no nearby algebraic terms that look like a over 1 minus r. So how do we get near? And we can use algebra or calculus. I just want to get to something that looks like a over 1 minus r. So our only handhold right now is forcing things to be looking like geometric series. We want to extend it a little bit more broadly, which we will in the next section, with not too much more difficulty at all. In fact, honestly, it's easier, I think, in 1110. I think this is hard, trying to force ourselves to fit a mold that isn't necessarily natural for this. And obviously, we're picking examples right here that are like one or two steps away from that, right? If I picked like the sine function, I really don't know how I would do today's techniques in terms of getting sine there. But some of these ones are nearby enough. So the thing that I'm thinking to myself right now is I know that the derivative of the tangent function looks vaguely correct. That's going to give me 1 over 1 plus x squared, which I'm going to think of as 1 over 1 minus negative x squared, which should then take me to the series from n equals 0 to infinity. A is 1, r is negative x squared, so I think I'm just getting negative x squared to the n. Why not, right? I'm just looking at my a term and my r term, and I'm writing them down in terms of my geometric series format right here. So that's pretty easy right there. And this is going to converge with a radius of 1 about x equals 0, right? So just like all the examples we've looked at today have been centered at 0 with with the radius of convergence of 1. Okay, we saw one that a radius of convergence of 5. It's not this one here. And notice that we didn't want this series right here. We just found the derivative of the function that we want. Now let's go out and actually get back h of x, right? So now let's take this integral of the derivative of h of x dx. This should be the integral of the series n equals 0 to infinity of negative x squared to the n dx right here. And what I think I want to do here in this case, by the way, sorry, I'm going to back up one step right here. This is the step that we're going to do. I just want to write this a little bit different so it seems a little bit more natural for us to write our steps right here. So what I'm going to do is I'm going to identify that this is really the series from n equals 0 to infinity of negative 1 to the n times x squared to the n, which is really the series n equals 0 to infinity of negative 1 to the n x to the 2n, right? So all I did was just kind of picked off that negative 1 to the n power and separated it from the other parts right there. The reason I did that is because I wanted this x stuff a little bit more simpler for me to integrate here. So it looks like what I can now do is take the integral of the series from n equals 0 to infinity of negative 1 to the n x to the 2n dx. And this won't be too bad at all for me to go ahead and integrate here. So it seems like I'm going to be getting just back recovering the function h of x because we took the integral of the derivative. On the inside here, I'm going to get the series from n equals 0 to infinity. The negative 1 to the n had nothing to do with the integration. Integration had to do with x. The sum has to do with n. Now when I take the integral of x, I should be getting a 1 over 2n plus 2, 2n plus 1. X to the 2n plus 1. And I think I now have a series. This is equal to tangent inverse of x for x being in the interval from negative 1 to 1. And remember, we always keep our parent interval, right? So since this guy converged with a radius of 1 about x equals 0, so too will our any derivative or integral of that same function right there. So I know this interval of convergence because I know this interval of convergence, and they were just off by one another by a calculus operation right there. So it seems like, I forgot an important thing right here. plus c. So now we can play that similar game of just saying plug in x equals 0, plug in x equals 0 to find c. Sum from n equals 0 to infinity of negative 1 to the n, 1 over 2n plus 1, 0. Two n plus 1. Well, it looks like 0 is just going to multiply all this stuff. And so it looks like 0 plus c is going to be equal to 0. So again, c is equal to 0 in this case right here. But keep not forgetting it. There are going to be scenarios when we get a non-zero c that's actually contributing some term. And so it does look like we're finally getting here that tangent inverse of x is straight up equal to the series from n equals 0 to infinity, negative 1 to the n, 1 over 2n plus 1, x to the 2n plus 1, for x being in the interval negative 1 to 1. And notice here, let's just always, I feel like always with these things, it's always worth it to write out some terms and see what this thing is going to look like right here. And it looks like, so when n equals 0, I'm getting positive. This fraction is 1, x to the 1. So my first term is just x. Then when n is equal to 1, we're getting negative 1/3 x to the 3. When n is 2, we're getting positive 1/5 x to the 5 minus 1/7 x to the 7th plus 1/9 x to the 9th. On and on and on out there, right? So that's literally our power series expansion for tangent inverse of x, and it should do exactly what tangent inverse of x does, as long as we are in that interval negative 1 to 1. So let's go pop over to Desmos one more time here and take a look. All right, so we've got tangent inverse of x. And we just determined that this power series should be, our first term was x. What a great way to start right there. Our second term should be minus 1/3 x cubed. And ooh, what a really nice cubic that is to match tangent inverse. Then we did plus 1/5 x to the 5th. And oh, that weird awkward bend that our look at that weird old bend that our fifth order is doing. It's a perfect bend to match the bends associated with tangent inverse. It's 1/7 x to the 7th. Oh yeah, that's real nice right there. Might have to go look at some of these graphs a little bit more later on my own. Oh, those are nice. And look, these are so much matching that there's a whole bunch of numbers where Desmos thinks that the black and purple graphs are actually intersecting one another, which technically they're not, except for at 0, 0 right here. But they're crazy close to the point where Desmos can't even tell the difference between the two at those locations. You can pretty easily visually see this negative 1 to 1 radius of convergence that we're getting for this one right here. And remember, I do think it is way easier for you to just straight up type these out by using sum and just do the sum. I typically always do A so I can control the slider right there, but we can always do this. Add the slider, and then let those A values get big, and you can see that we're doing exact same things right there. So here's our 10th term in the series out there. That red curve is doing even a little bit better than the black curve was doing in this diagram right here, because we've gone 10 terms out instead of only 5 terms out right there. Right? Really, really, really cool stuff here. So you should be very excited that, one, we now have a way to represent some functions in terms of power series, but right now we're limited by the fact that we need to either be algebraically nearby to a over 1 minus r, or we need to be in terms of calculus nearby to 1 over, or to a over 1 minus r. And if we're not nearby to either of those, if we're not nearby in either an algebra sense or a calculus sense, we don't really have a way to do this otherwise yet. So what we're going to do in the next video is we're going to say, well, shouldn't we be able to generalize this to more functions? And once again, I would say to you, what would you do right now if I said come up with a power series for sine of x? I just don't know what I would do to force this into looking like some form of a over 1 minus r. It's not nearby to that in terms of algebra or calculus. So what we're going to get in the next video with our Taylor and Maclaurin series, our final video of the semester, is that we're going to see how can we do this more generally without having to play these kind of silly games of trying to match up to a geometric series all the time. I want to just do some math and say, there's the series right there. And so I honestly think section 11.10 is going to be actually easier than some of the stuff right here, because this requires some sort of like, these aren't tricks, but like, you got to be a little crafty to kind of think about these maneuvers that we just did with like tangent and with natural log and stuff like this. But again, I hope that you also see the huge power of this. This is massively powerful that we're coming up with polynomial ways to represent non-polynomials, rational number representations of irrational numbers. This is taking the hardest parts of math and representing them in terms of the easiest parts of math. This is wildly powerful right here. So this is, like I said, this is a skill that everybody's going to expect that you have to some degree leaving this course here, some understanding of Taylor series and why they're valuable. They turn everything into the easiest thing that we can possibly want to deal with. And I'm going to say one last comment right now. Not only are they turning us into something easy like polynomials, it's also giving us like a common ground. So now when I want to deal with expressions that involve perhaps both sine and e to the x and natural log, and if I were to say to you, hey man, solve that equation for x, you straight up can't, because there is no algebra or trig maneuvers that are going to kind of work those things together. However, if we could convert all of those things into polynomials, that is now one common ground for all of them to have a polynomial representation. Maybe then we could go about solving some equations that involve terms that you otherwise had no way to combine up until just now. So that's going to wrap it up for me here today with our power series. In our next and final video, we're going to look at Taylor and Maclaurin series, which are a more generalized version of this, where we're not so committed to this whole a over 1 minus r requirement. We're just going to find the series for any function out there, and they might have good or bad intervals of convergence. We'll kind of, that's going to be what it's going to be, but we're going to be able to do this with a more general process that's actually really, really easy to do, and that's going to be in our next video there. I will see you guys for our final video, 11.10. Have a good one, everybody.